Hello! I've recently been playing around with ray tracing. Ray tracing is a rendering technique that involves shooting rays out of the camera until it hits an object and then computing the lighting information at that point. But wait, why do we shoot rays out of the camera? In real life, light propagates from the light sources to the camera. If we shoot light rays from the light sources, we waste a lot of resources tracing rays that never hit the camera. If we on the other hand shoot rays from the camera, we are guaranteed to get what the camera is looking at. When implemented, ray tracing can produce beautiful images. But we have to start small. Let us see if we can render any geometry. For simplicity, let us start by rendering a sphere. For this, we need to define a ray class and a sphere class. The ray class is very simple. We represent the ray as a point and a direction vector parameterized by t. We can then compute the point P the ray is at a time like so. For any primitive in the ray tracing, we just need two functions. First, we need a function that computes the intersection with the ray. Secondly, we need a function that computes the normal at the points on the surface. For the intersection, if the ray missed the circle, then there's no intersection. If the ray hits the edge of the circle, there will be one intersection. Finally, if the ray hits the middle of the circle, there will be two intersections. Now we'll have all the pieces to render a sphere. It doesn't look like much, but it's an actual ray traced sphere. For the color, we just render white if the ray intersects the sphere, and a black otherwise. We can also render multiple spheres by looping over all the objects and seeing which one is the closest one. In real life, objects are not just one color, they're shaded according to light direction. But this requires us to create some lights. For simplicity, we will stick with white point lights with no fall off. Then we just need the light direction from any point. But how do we compute the shading? If we take a step back, we notice that if light hits directly at the surface, it should reflect with the full intensity. Whereas if the light hits at a steep angle, it's more shaded. We can capture this relationship by attenuating the light by the cosine of the angle between the surface normal and the light direction. However, this has two problems. When the cosine is negative, the light will darken the object instead of brightening it. We can solve this easily by applying the shading only if the cosine is positive. The other problem is that the far side of the circle will not get any light and will therefore be completely black. This, however, is not very realistic outside the solar system because light from other objects in the scene will bounce around and illuminate the dark parts. This is called indirect lighting. To simulate this, we'll cheat and add some ambient light to the material that will be added regardless of the light contribution. This already looks much better, but in real life, objects are not just matte, they have some shininess or specular highlights. Specular highlights depend on the view direction, so we need to compute the direction from the intersection point to the camera. We also need the reflected ray, which we can compute using the law of reflection. Then all we have to do is attenuate the light by the dot of the view vector and the reflected vector, and then raise it to some power which determines how concentrated the specular highlight is. We now have successfully implemented the Phong lighting model, which is the ambient color plus the diffuse color plus the specular highlights. Why so simple? This model can approximate many real-world materials. Right now we have light but no shadows. This is not very realistic, so let's add some shadows. But how do we go about that? When we hit a surface, we can loop through all the lights in the scene and ask if the view is obstructed by casting a ray between the intersection point and the light source. If the view is unobstructed, great, we can add the light contribution to the object color. However, if the view is obstructed, we just add the ambient light color at that point. We notice that the shadows are hard. We'll address this later, but they are caused by the fact that the light is a point light. Moving on to tackling reflections. Computing reflections is very similar to how we computed the specular highlights. We need the reflected vector and then send out a new ray from the intersection point in the direction of the reflected vector and compute the reflected color. Then we mix the color according to the reflectance of the object. The reflections with the black background is a bit boring, so to make it more interesting, we can add a background. But how do we do this? We can use cube maps, which are textured cubes, and project them onto a sphere, then ask what color the texture is in the direction of the ray when it doesn't intersect any objects in the scene. It took me a while to get the projection right, but in the end we have a working cube map skybox which gives us interesting reflections. We now have a fully featured ray tracer, but while the renders look good, we're cheating a lot by having the ambient color instead of getting true global illumination. Luckily, there's a simple extension to ray tracing that allows us to get global illumination: path tracing. The main difference between ray tracing and path tracing is that instead of just shooting one ray per pixel, we stochastically shoot many rays per pixel and let them bounce around in the scene, hoping we hit a light instead of specifically seeking out the lights. This also means that path tracing doesn't work with point lights, as the probability of hitting a point is 0. So instead we add an emissive property to our sphere material so we can use the spheres as a light source as well. However, since we're sampling many times per pixel, path tracing is computationally much more expensive than ray tracing, and with our current Numba implementation it's simply too slow. So before we adopt a new light transport, we need to speed it up. To speed up the code, we'll use Numba, which compiles Python code to speedy LLVM machine code and gives us parallelism for free, which is very handy since the entire path tracing algorithm is completely parallelizable per pixel. Having spent a lot of time dealing with the limitations of Numba and its type inference system, I finally got the speed up I wanted. The render times are now 10x faster and could be faster if we ran it on the GPU. So now we can focus on refactoring the light transport to be compatible with path tracing. Specifically, we should define how the rays should bounce. For reflectance, we can use the same source code as before. We use the same technique for specular highlights as well. However, for diffusion, we should sample the direction uniformly from the hemisphere above the surface normal. This doesn't look that good, but that's because we haven't tweaked the parameters yet. The last thing we need to tackle is refractions. Refraction happens when light travels through media with two different refraction indices bending the light on its way. We should obey the Fresnel equations, but to simplify a bit I used a slick approximation for the Fresnel factor. This leaves us with a pretty featureful path tracer, however there are more things we could do. I did work on a couple of more features which I wasn't able to figure out how to implement correctly. The first feature is caustics. I thought caustics would come for free when you implement refractions correctly, however I haven't been able to observe caustics in any of my renders. I thought perhaps I implemented it wrongly, so I borrowed someone else's code and integrated it into my rendering pipeline, but I still wasn't able to observe any caustics. I know that backwards path tracing, where we shoot the rays from the camera, is terribly inefficient at rendering caustics, and we should ideally be using bidirectional path tracing or photon mapping to get caustics. However, I have seen renders using backwards path tracing to get noisy caustics, so the fact that I get nothing puzzles me. Really, if you have any insight, please contact me. The other feature was implementing arbitrary meshes, which I did get to work but was terribly slow, so I tried to speed it up by constructing a KD tree for the triangles. However, something's wrong with my implementation of the traversal. I might return to this someday as it bugs me that I didn't quite reach my goals, but for now it's a pretty fast path tracer implemented from scratch in Python.